be comparing means, and so we have to remember that our procedures are pretty similar to before, except for in the nearly normal condition, do not check n times p, n times q. That is for proportions. And we are not using proportions here. We are using means. So we're thinking about central limit theorem. But we know that t is equals robust. And especially in these two mean situations, either all the way down to n sub 1 equal n sub 2 equal to 5, when you have the same size in each sample group, t distributions are extremely robust all the way down to a level where both things are 5. So anyway, we still need to have random. We still need to have independent. And that is going to help us with calculating the spread. And now for the spread of two means, again, combining through variance. Remember those chapter 6 methods. We, even though we're doing the difference, we still notice that it is addition. And then this formula is on the formula sheet. And then the mean formula is on the formula sheet. So glance at your formula sheet and you will see your symbols for these two things, this one being x sub 1 minus x sub 2 with the bars on top, and this one being the mu symbol with the x sub 1 minus the x sub 2 with the bar on top. And again, like, we're not going to write it like this because that is a one sample where you probably had paired values and you did the subtraction before you did the summary stats. So don't write it like this. This is how you write a two sample difference. Okay, so if we know sigma, just like before, if we know sigma, then we will use the z interval or a z-test as appropriate. But normally we will not know sigma. Then you must use your sample statistics. And so the AP test, the AP exam or test asks you to use a t-interval and a t-test. Those are what are appropriate. Okay, so this just summarizes the formula for if you are doing a confidence interval, a two-sample confidence interval for the difference of two means. And remember that this is your margin of error. So your margin of error is going to be that critical t value at whatever alpha you're at, and your standard error for your difference of two means. And that's going to be found with sample values. You can see the sample values in there. And this is going to be your difference of your two means. And then, adding and subtracting the margin of error, which is this part right here. This is the margin of error. This is your point estimate. Okay. So the degrees of freedom will be, if we're doing it by hand, we're just going to go with the smaller of the degrees of freedom from using the first sample group and the degrees of freedom from using the second sample group. We'll notice that when we use technology will actually have a different degrees of freedom because there's a very complicated formula. t-intervals and t-tests are so robust that they actually can adjust the degrees of freedom to something larger than what you have. But it's a very complicated formula, one that we wouldn't do on our own. So these values are going to be very conservative. But we'll notice that when we use technology, we'll get a different value. So if you use technology for your result, then you will want to say with technology next to your answer. Because df will be larger. Okay, and we'll do some examples of that. Okay, so we need to be random. We need to be nearly normal. We can meet CLT, or we can show that it's normal. Well, it can be either normal, or we can meet CLT, or we can use the process down here. Okay, independent. That has to be for each group, meeting that 10% condition. Okay, so this says that the T procedures are more robust, even at very small sample sizes. Now, reviewing from Chapter 9, when we are less than 15, especially in the cases where we don't have them matching exactly, then we will want to avoid things that have clear skew, and we definitely do not like outliers. If our sample size is at least 15 but less than 30, then even with some skew, that will be fine. But again, we do not use these procedures if we have outliers. And if we have a large sample, then a 2-sample T procedure can be used, even if we have very clear skew. Again, in the case of outliers, generally you would run the test twice, once with the outlier, once without, and see how the results compare. So when n is less than 15, when we are between 15 and 30, and then of course we meet CLT when we are over greater than or equal to 30. Okay. So in planning a two-sample study, it is very nice to choose equal sample sizes in your two groups. Because when you do, having equal sizes will make this whole test more robust. And interval more robust, even for small sample sizes. We will never pool in means. That is only a test of proportions where h sub 0 is equal to 0, the difference of the proportions is 0. So that's the only time. Never, ever, never pool means ever. Okay, we are safe using 2-sample T procedures for comparing two means in a randomized experiment. And in that, we the independence will be fulfilled by random assignment. And also the thing is, because you have an experiment, you can establish cause and effect. Okay, so that's something very interesting. And then you want to beware of making inferences in the absence of randomization. So we saw that, like, if you have something that's convenience, or you have under coverage, response, well, response bias is terrible because that means you're getting some lies. So I don't really like that one because that's just plain old lies. But if you have non-response because you don't know why they didn't reply to you, why didn't they reply? Were they not home? Were they not willing to answer? Or were they voluntary response where those people have strong opinions and that's why they're willing to come forward? Under coverage is you left out an important group. So, like, when you have absence of randomization, these kinds of things can happen where you will have bias, and you must report direction of bias. Give the why. All right, and then do not use two sample t procedures on paired data. That same thing goes with the proportions. Don't use two sample t procedures on paired data. Make sure that you are looking at make sure you examine what you're actually looking at here. Are you looking at an individual drinking coffee and not drinking coffee? That would be one individual. You want their result, and you're going to compare it to the results for other individuals. Or are you looking at all these people drink coffee and all these people didn't drink coffee, and you're comparing the groups? So make sure you can tell the difference. So here's an example. Literacy rates were collected for men and women in 5 countries. Describe your inference procedure. In this situation, you probably would have the country 1, for example, and you would probably go men minus women, and that would give you a result, right? And then you would have then compare results for each country. So that means you did the subtraction first. That would be a 1 sample procedure. Okay, now if we have these participants and they have been randomly assigned to the ABC reading program and the XYZ reading program, after 4 weeks, the results are collected for each group, and then we're going to compare. In that case, we're going to go ABC, and we're going to get our results. And we're going to go XYZ, and we're going to get results. And now what we're going to do is we're going to compare final ABC to final XYZ. That is a 2 sample procedure. Okay, so let's just, based on this information from the U.S. National Health and Nutrition Examination Survey, we've got heights, they're normally distributed. We've got 10-year-old boy heights, they're normally distributed. the researcher is going to take an independent SRS of girls, 12 girls, 8 boys in this age, and examine their heights. It would be nicer if they had done 12 and 12 or 8 and 8, because that would have increased how robust it is. But those numbers are fairly close to the 15, so we would want, but and they did say that it's already nearly normal, so we're already normal, so that's good. All right, so let's do number 1. Okay, describe the shape, center, and spread of the sampling distribution for the difference of the mean heights of females and males. Okay, so 1, the shape. Well, males were nearly normal, and the females were normal. Okay, therefore the shape of the difference in the sample means will be nearly normal since the genders are given nearly normal. So if you're nearly normal before, when you combine together, you are still nearly normal. Okay, now the center. So let's see, means, and why don't we go females minus males? And that is going to be the difference in the mean female height minus, I guess I didn't really need to say the word minus the mean male height in, I don't know what the units are, inches. Okay, so mu sub F is female height. Mu sub N is male height. Again, those are in inches. Okay, and so let's see the center. The center. Okay, this is the center. This was the shape. Center. It will be mu F minus M will be, what was the numbers? They were 56 minus 55. So that's going to be, wait, 56.4. Let me write that over. 56.4 minus 55.7, which is 0.7 inches. Okay, the center of the difference in female to male heights is 0.7 inches. Okay, spread. Okay, so we go to the formula sheet, and we see on the formula sheet, it looks like this. Of course, I'm putting the F and the M in there myself. Okay, they're going to take the female heights over the N for the females, and we're going to add it to the male heights. There's no pooling ever in this nature of this situation, so let's put these numbers in. 2.7 squared over 12 plus 3.8 squared over 8. That's 1.55322. That's probably long enough. And that's also inches. Okay, there's question 1. The shape was nearly normal. The center was at 0.7 inches, and the spread was that it varies from the center of 0.7 inches. It varies by approximately 1.55 inches. Of 1.55 inches. Okay, wonder what that square is. Okay. All right, now let's do question number 2. Find the probability of getting a difference in the sample mean that is less than 0. So females minus males being 0. So we have established that it's nearly normal, but I do need to establish that it is random, and that was given in the problem that we did in SRS of the boys and the girls. And now we need to be independent. And since this is not an experiment, I will check it. And let's see here. Independent is 12 less than or equal to 10% of N for the girls, plus girls in the world, and is 8 less than or equal to 10% N for the boys. There are over 80 boys. Yep. All right, plus girls. So that meets our independent condition. So conditions met. And we're not doing a test or an interval. They just asked us to find a probability, so I don't need to write the name of the test. I'm just going to draw my probability. The mean will be what I found the center to be at, which was females minus males. And I'm going to just say that that's 0.7. And I want to know the probability of getting below a 0. So let's do the z-score for that. Okay, 0 minus 0.7, right? Hypothesized value minus parameter value, or statistic value minus parameter value. The hypothesized value is usually your parameter value. Okay, and then let's put the standard error, standard deviation of the sampling distribution down here. Okay, z, negative 0.450676. Now let's find the probability of that. Probability that a z goes less than a negative 0.450676 is 0.326. So the probability of getting female minus male height difference of 0 or less is 0.326. Okay, that takes care of part 2. You probably have run out of room, but let's do part 3. Luckily, won't take very much room at all. Part 3. Now they're asking, does the result give us reason to doubt the researcher's stated results? The researcher reports that the sample mean height of boys is larger than the sample mean height of girls. That's what they're reporting. So, look at that probability. That's not unusual. Okay, because the probability of 0.326 is greater than 0.05. This does not appear unusual. Therefore, I do not doubt the researcher's claim. The evidence does not, because it's really a lack of evidence, the evidence does not make me doubt the researcher's claim. Boom. Done. I don't know what this square is. Okay, so now we're going to compare the means of these two tracts of land in the Wade Tract Preserve in Georgia, which is an old growth forest down there of longleaf pines, and it's survived in a relatively undisturbed state for hundreds of years. We want to know, are the sizes of the longleaf pines different in the two different forests? So they have summary statistics for each of the forests. We've got our means, we've got our standard deviations. They took a random sample of 30 trees. Here are some box plots so that we can take a look at this, and I see that there are no outliers, which is something good. Okay, so let's write out all their information about these things. Let's see here, north. So mu sub n will be, I'm going to use a capital N, will be the mean dBH for northern trees. And that'll be in centimeters. It's very important to have units when you're talking about means. Little subscript S. This will be the mean dBH for southern trees. And that's going to be in centimeters. We have, let's go through our conditions here. Why don't we write them at the top here? So first of all, we need to be random. And they did say it's an SRS into forests. So that is given. Is it independent? We have to check it for each group. And I would say that 30 is less than equal to 10%. And if both forests each have over 300 trees, because like they both were at 30, so I'm just doing that, writing that once. And then is it nearly normal? And that is met because of the meeting CLT. CLT is met since both groups had 30 trees in sample, and there was no outliers. That's good in our data. So that means that our conditions for inference are met. And T would have been quite robust, especially at that level of 30, where these are both the same matching. It would have been really robust even at a lower level. So we will do a two-sample t, because we have unknown sigma, we're using sample values. T, what do they want us to do, an interval or a test? They want us to do a construct an interval, t interval for difference of means. And we're specifically going to do, why don't we do we want to do north minus south or south minus north? I mean, it doesn't really matter, but why don't I just go south minus north, because then I'll end up with positive numbers. So southern DBH minus northern DBH, because it looks like the south might be higher. So since we're doing an interval, that means we will use the sample values for our point estimate. So x bar s minus x bar n gives us a 34.53 minus 23.70, which is 10.80. That's our best point estimate. Now we're going to find our, because remember, you do your statistic plus or minus your critical value. Whoops, in this case it's a t, not a z. I was about to write a z. Critical t. And then in here you're going to have your standard error for your south minus north. These two things being together making up the margin of error. But let's go through and find our critical t. So degrees of freedom, well, both groups are n minus 1 is 30 minus 1, which is 29. Degrees of freedom n sub 2, south and north, minus 1 equals 30 minus 1, which is 29. So no matter what, we're going to be using 29. They want us to go with a 90% confidence interval. So alpha is equal to 0.10. So 0.10 divided by 2, 29. And that critical value coming out of the calculator using inverse t, 0.05, comma 29, or a table, but calculator's way faster, you get 1.6991. Okay. We need our standard deviation for the, or standard error for the sample difference. Okay, so let's do that. We're going to get our standard error for, and I'm just looking at my formula sheet to make sure I'm writing this right. So x for the south minus x for the north, because we decided to go that direction. Or I guess I just did. And so we're going to take the sample south value, square it, put it over the sample south n, sample north value, square it over the north n. Those numbers in. Let's see here, we got a 14. Okay, 14.26 squared over 30 plus 17.5 17.50. Sorry, I can't see the top, squared over 30. Take the square root of that. It's like this is the square root of that. Okay, so then that gives me, let's see if we can see this. That gives me 4.121478. Okay, so now let's take the mean difference. That's your statistic, which is 10.83. Let's add and subtract that critical value. and in this case a t, which we got as 1.6991. And so that's that right there. And then we've got our standard error of statistic, which we just found is 4.121478. And we're going to add and subtract these two things, and I'm going to write my mean south minus mean north. Notice that I write them separately because this is a 2-sample situation, not a 1-sample. 3.83, of course these are in centimeters, and 17.83. So with 90% confidence, the interval from 3.83 to 17.83 centimeters captures the true mean difference in dBH measurements for south minus south and northern pine. What are they? Longleaf pines in the Wade Forest. Okay, I'd say that's probably pretty good. Okay, and then if I want to do this with technology, you're going to notice that I'm going to get a different answer. So the answer with tech, which I'll do in just a moment, it comes out as a confidence interval of 2.573, 19.09. So it's a little bit narrower, and that is why, because the degrees of freedom, because it's so robust, the degrees of freedom from technology are much larger, giving you a narrower window. So I would write with tech so that it's clear how you got an answer like that. And so I can write that again if you prefer to see it with the subscripts, in the interval form. Okay, so now I'm going to do it with technology. I hit stat, and now I go over to tests, and I can see that these are my two tests, but I don't want a test, I want an interval. That's a 2-sample Z interval, but I want, there's my 1-sample intervals, but I want a T interval. So I click on T interval, and I tell it that I want to do it with stats, and I've already started entering it in, but I don't think I have it completely in. So there's north, which really I should have put south into there. Oh yeah, I did put it all in. And you're going to never pool on these tests for our purposes. So no pooling, go down and calculate. And so that gave us the results. And, as you can see, it's just been flipped around because I flipped the order of the north and the south. That's why it's so important to say what one you have.